Welcome back. Our long and exciting journey into section 2.2 continues. Yet another and several more still videos related to section 2.2. So let's dive in now to case 3, complex conjugate roots, and back to our original constant coefficient, second order, homogeneous ODE for y as a function of x. That's what we're using here. There are usual conditions on the coefficients, and we get our characteristic equation, right? Another word for it is the characteristic polynomial, right? It's a polynomial. What degree polynomial is this, Renard? Good, it's second degree, it's a quadratic, right? Okay, quadratic equation, quadratic polynomial, therefore our quadratic equation allows us to solve this guy in general. So we're going to get this quadratic in the case of a second order constant coefficient ODE, right? We've done case 2 and case 1 where this characteristic polynomial produces, in case 1, 2 distinct real roots, and in case 2, a single repeated real root. And we know what to do now in those cases and how to get the general solution. And today we begin to investigate what happens in case 3 when we have the case of complex conjugate roots. And that's going to be the case where our discriminant, remember R, is minus b plus or minus the square root of b squared minus 4ac all over 2a, right? We don't really care so much about that. We generally aren't using that, right? But what puts us in that case when we're in the case of b squared minus 4ac negative, right? When that guy is negative, what we get out is 2 complex conjugate roots. So R1 is some alpha plus I beta, and R2 is alpha minus I beta. What? Right? Okay, we'll explore that in just a little bit. So what does that mean? We can say that more simply by saying R is alpha plus and minus I beta, because they're complex conjugates of each other. Refresh what that means. What does that mean? Alpha and beta are real numbers, okay? Well, the last videos we were using alpha and beta as our initial conditions. That's clearly not what we're using them for here, right? Okay, so what is I? Well, you guys kind of know what I is. We can write this. We're going to talk about that a little bit later. I is the square root of -1. That's nice notation. Anyway, we'll talk about that notation in just a little bit as well. So really what we're going to do is kind of get a little more comfortable with complex things. And let's do that in the context of a specific example. So let's start off with a specific example so you can see some numbers instead of just some letters, right? Okay, so let's consider the ODE let's do 2y double prime minus 2y prime plus 5y is equal to 0. Okay, let's go with that. Okay, 2, 2, and 5, they're kind of nice numbers, right? That doesn't look so terrible, right? This is, find me all functions out there in the world where twice their second derivative minus twice their first derivative plus 5 times themselves is 0. But when we say out there in the world, we mean out there in the real world, right? We're starting with real number coefficients, right? A, B, and C, 2, -2, and 5. And we would like solutions for y as a function of x that are real valued solutions. Solutions like we use for functions in Calc 1 and Calc 2, right? That is, we do real valued calculus, real valued functions, right? Of a real variable, okay? So what we would like to come out of that would be keeping it real, right? Okay, so let's take a look. What is our characteristic equation then for this nice innocuous looking ODE? The characteristic equation will be, you guys tell me, you should be able to rattle that off really fast right now, right? Good. 2r squared minus 2r plus 5 is equal to 0, right? Quadratic polynomial on r, where we determine the values of r that go into e to the rx, right? Okay, well, let's see, like, you know, what would you do? You know what case we're in, so you kind of know where that's heading, but, you know, you would just normally just think about factoring, right? If I'm thinking about factoring, I'd be like, okay, well, it's 2r, so it's going to be 2r and r, right? And then my only options, right, this is a plus, and that's a minus, right? So that's going to have to be 2 minuses, and then it's 5, so, you know, it can either be 5 and 1. Is that going to work? No, minus 5r, minus 2r is minus 7r. Nope, that's not working. Okay, well, what about then 1 and 5? So minus r, minus 10r, that's minus 11r. No, so that's not factoring, right? So it's pretty clear this guy isn't going to factor. We can double check, right? B squared minus 4ac. What is b squared minus 4ac? What is b? Good, careful. Negative 2, right? So negative 2 squared minus 4 times a, which is 2, and c, which is 5, right? Okay, so there we go. We got 4 minus 4 times 10, yeah, okay. Now, we could actually, like, make it 4 minus 40, but, you know, just for fun, that's all. Obviously, 4 minus 40 is negative 36. Another way to get that is it's 4 times 1 minus 1 minus 10, sorry, jumping ahead, 1 minus 10, which is 4 times negative 9, right, which is negative 36 as well, right? Okay, just thinking about factoring. Anyway, regardless, any way you slice it, negative 36 is negative, right? And therefore, the discriminant here in under the square root is negative, and that's going to produce imaginary numbers, right? Okay. So we know then we're in that case where we have our complex conjugates roots, so let's see what they are. So what are we going to have? So what are our r's? Well, they're minus b, okay? So what is minus b? Minus b minus a minus 2, right? Just making sure you see where it all comes from. Minus a minus 2, that's what b is, right? Plus or minus the square root of b squared minus 4ac. We already did that. That's negative 36, yeah? Okay, all divided by 2a, what was a? 2, yeah? Okay, all right, so let's do the math here. What are our r's? So we got 2 plus or minus, what is the square root of negative 36? Good, right? So we can think about the square root of negative 36 as the square root of negative 1 times the square root of 36, right? Because the square root of negative 36 is the square root of negative 1 times 36, and we know that the square root of the product is product of square roots, right? And here things are getting a little crazier. This is the thing we call I, right? I times the square root of 36. The square root of 36 is 6, right? So 6i. Yes? Okay, square roots are positive, right? Okay. Okay, so what do we have here? 6i all divided by 4. Yes? Okay, so then what do we have? Well, that's 2/4 plus and minus 6/4 times I. Yes? 2/4 simplifies, that's 1/2 plus or minus 3/2 times I. So there's our two r's, right? So for this problem, what is alpha? 1/2, and what is beta? 3/2, right? We have two roots, alpha plus I beta and alpha minus I beta, right? So our two roots are 1/2 plus 3/2 I and 1/2 minus 3/2 I. Yes? Okay. Okay, well, what do we do with that, right? That's not wonderful because, you know, the idea is what are we going to do? We're going to put that R up here, and then that's going to give us complex valued solutions, right? So let's just write that down so that we see what actually happens. So you know, our R1 is 1/2 plus I, 3/2 I, right? 1/2 plus 3/2 I, and our R2 is 1/2 minus 3/2 I, right? We usually write it when we have a number, we usually write the number in front of I, but when we have a letter, we usually write the letter after I. Alpha plus I beta instead of alpha plus beta I. Usually, I don't know, maybe you do it both ways. Anyway, it doesn't really matter. These guys are complex conjugates, right? R1 and R2 are elements of the complex numbers, right? Okay, so we're gonna talk a little bit more about what that means, okay? What do we know about this parabola, right? This parabola, well, this guy, he opens up, right? And so, you know, since it's an opening up parabola, it must live up here somewhere, right? It turns around, it never intersects the R-axis. There's never any real number for which it has a root, right? So it has two imaginary roots, okay? Complex conjugate roots that do not live on a real line. And in fact, this whole quantity is always positive because it's got to live up there, right? Okay. So now what? Well, what does that mean? Okay, so we're back to here, and we're just like, well, so what do we get out of this, right? Well, then for this problem, we would get like one solution. I'm not going to even write y1 right now. One solution is e to the r1x. Well, what is e to the r1x? It's e to the 1/2 plus 3/2 I x. Ooh, we're not liking that. And second solution is e to the r2x. So that's e to the 1/2 minus 3/2 I x. Now, these are complex valued solutions to our ODE here, right? But we want our y to live in the real world. We want y to be a real valued function, okay? And so here are our solutions. These guys are legitimate solutions to this differential equation. They solve, but they're complex valued functions that solve this differential equation. So our question is, can we come up with just real valued functions that solve the differential equation? Or are we stuck with nothing but complex valued solutions to the differential equation, okay? So let's just talk a little bit about some notation first. So right now, instead of, so our question is, are there real valued solutions? That's what we want. So when we put in an x, we get out a real number. Instead of when we put in an x, we get out a complex number, right? Okay. So we're not actually going to address that just yet. Let's get a little more comfortable with complex numbers first, okay? So now we're going to just leave this problem, and we may not even come back to it this video. We may even have to wait. That could be fun. We may not even finish this concept with this video, especially if I try to keep this video a little shorter, and we'll come back to the finishing out this concept in the next video. All right, so let's talk about a couple of things. We use this notation, so if I say the real part of R1, for our R1 that we just had in there, so I can just erase this here so I have it. Let's see, look how cool that is. Now I got R1 and R2 standing there staring at me. Yep, awesome. Okay. So here's R1. What is the real part of R1? The real part of R1 is 1/2, right? And that's also the real part of R2, right? I can ask for the imaginary part of R1. What is the imaginary part of R1? It's 3/2, okay? It's the real number, right? That is with the I, yeah? And what is the imaginary part of, what is the imaginary part of R2? Minus 3/2, right? Okay. Okay, more notation for these guys, right? We said these two are complex conjugates. More notation for that is that R2 is the complex conjugate of R1, okay? So what do we mean if we look at the complex conjugate of R1? That means we just change this plus to a minus. Yeah, okay? So the conjugate of R1 is 1/2, which is R2, right? And what is the conjugate of R2? Well, good. You change this sign minus to a plus, right? Okay, which is R1, right? So that's why we say they're conjugates of each other, right? Okay, R2 is the conjugate of R1. R1 is the conjugate of R2, right? So what is the conjugate of the conjugate? What is the conjugate of the conjugate? Itself, right? Yeah? Okay, good. All right. Anyway, what else can we say? What do we want to talk about? So that's notation that we'll often use. There's lots of ways to define what the complex numbers are, but I mean, just think of them like this. Here's the complex numbers, and the real numbers live inside, right? Okay? So if I'm a complex number, a lot of times, we'll use the letter Z to represent a complex number, okay? Z is often some alpha plus I beta, okay? And so the real part of Z is alpha, right? The imaginary part of Z is beta. These two things are real numbers, okay? The real part and the imaginary part are real numbers. And then I is our guy that we're about to talk about a little bit more, okay? We often say I is the square root of -1, okay? So a purely imaginary number, purely imaginary, as opposed to complex number, would have a 0 real part, right? Okay, so a purely imaginary number, there we would have just something like I beta or beta I, right? Same thing, yeah, okay? So for that guy, the alpha, the real part would be 0. If Z is a purely imaginary number, the real part is 0. So in this case, alpha would be 0, right? So what is a real number? A real number is a complex number whose imaginary part is good. 0, right? Okay? So if beta is 0, if the imaginary part of z is 0, then z is just a real number alpha, right? Okay. Let's see, what else do we want to talk about? Let's talk a little bit about I now, okay? Let's talk a little bit about I. So if we're gonna have any hope of exploring this concept of are there real valued solutions to, you know, our sample ODE or in general ODEs that fall in this case for constant coefficient ODEs, we better know a little bit more about I, okay? So let's talk about I. Let's talk about I, right? Okay. So, got our guy I, okay? I squared, well, what does that mean? That means I times I, right? Okay? Now, what is I squared? Good. I think I heard it out there. We usually say I squared is -1, right? Okay? I squared is -1, which is why we often write I as the square root of -1, right? Because that makes sense to go from here to there. Yeah? But what is really going on with I? Okay? So let's just take a look. So suppose I have a vector, like say V. Say this is a vector V, and it just sits right here in the, you know, pointing right here, some length, and points in this direction. Then what is IV? Okay, what does I do? Well, the application of I to a vector, this rotates. So geometrically, I is extremely interesting and maybe, you know, a lot more so than what is happening over here. Anyway, IV rotates a vector V counterclockwise through an angle of 90 degrees. Right? So, if we believe that, trust that, then what happens? If I apply I to V, then what happens? That's 90 degrees, right? And then here it becomes V. Yeah? Let's pretend it's the same size. Okay, I was just trying to make it bigger so you could see it. Okay? Okay, here's my vector V. So what is this one? This guy is IV. I applied to V. I took that guy and rotated it counterclockwise through 90 degrees. Okay, well then, what if I do that again? What if I apply I to IV? What's gonna happen? Yeah? It's gonna take IV and rotate it counterclockwise 90 degrees. Here. So this is I applied to IV. But I applied to IV, well that's, in shorthand, I squared V, because we applied I twice on the left, and it matters, okay? That's another class. Anyway, I squared V is this vector, but what do you know about this vector compared to this vector? They're the same length, but they point in the opposite direction, right? So if this guy's pointing this way, this guy is minus V, right? So geometrically, right, this thing is minus V because we flipped it and made it point the opposite direction, yeah? 180 degrees. Okay, well if I squared v is equal to minus v, right, then that's the same as minus 1 times v, and therefore we kind of get the fact that I squared is negative 1 in a geometric visual way. Okay, so that guy really has a lot more cool, interesting geometry associated with it, but we won't just spend too much time talking about that. So let's keep going with this right now. Okay, well, so what if we do I cubed then? Well, I cubed is I applied to I squared, right? Okay, I times I squared, right? Visually, what would we get? I cubed v would bring us down here, right? Yeah? Okay. So I cubed v is really minus I v, right? Well, let's see if that's what happens, okay? So what do we have? We have I, what is I squared? I squared, so we can think about it as I squared times I, right? If we're doing it more algebraically, right? We can alternate those guys with rules of algebra, different order. I squared, we just said is negative 1, right? So that's negative 1 times I, which is negative I, okay? And so we just said, right, this guy would be minus IV, right? I cubed applied to a vector v would be minus IV, because that's that guy heading the other direction, right? Okay, and that's equivalent to I cubed v. Hey, this is kind of cool. All right, so what should I the fourth be? We apply one more, what do you get back what? Back to where we started, exactly, right? One more rotation, I the fourth v should be 1. I the fourth should be 1, and indeed it is, right? Lots of ways to think about it. We can think about it as applying another one of those, or we can think about it as I squared times I squared, right? And what do we know I squared is? Negative 1, so that's negative 1 times negative 1. Negative 1 times negative 1 is 1, right? So if we applied I to the fourth to v, we would bring it back to where it started, right? We'd be back to where we are. And we can keep doing that idea, okay? So this concept about complex variables and I as a rotation, these ideas are central to animation, and lots of linear algebra is central to that as well. All your video games and fun animated movies. Couldn't do it without I. Anyway, let's keep going. So now what? So we got I to the fifth. Okay, well what's I to the fifth? Well, it's I to the fourth times I. Yeah? Okay. What was I to the fourth? 1. So what do we got? I, right? 1 times I, which is I. Yeah? Well wait, now we're back to where we were. Yeah? So if I do I to the sixth, then what? Well, that's I to the fifth times I. What was I to the fifth? Right? I to the fifth was I, so that's I times I. That's I squared, that's negative 1. Yeah? Okay? Same deal. Right, what's I to the seventh gonna be? Good, negative I times this guy, right, is gonna give me negative I. What's I to the eighth? You wanted to sing a song here, but I won't. Multiply that guy I, minus I squared was, I squared is, let's just raise that. Right, I to the eighth is I to the seventh times I, that's minus I times I, minus I squared is negative 1, minus negative 1 is 1, right? Okay, so what is happening when we take these powers of I, we rotate through I, negative 1, negative I, 1, I, negative 1, negative I, 1, and that would just continue on and on forever, right? Okay, that's going to be pretty useful to us soon. And so, you know, because of all of this piece right here, we often call I the square root of negative 1, since the square I times I itself is negative 1. But that's kind of more of a notation, a convenient notation. It's really more of a whole cool, incredibly amazing concept. The geometry of I makes a whole lot more sense. It's very visual, and then you know you got to develop an algebra that goes with all of that, and you know, this hasn't been around all that long, right? I mean, you know, 500 years ago, maybe, when kind of this entered the scene, maybe not even. And nobody believed it, trusted it, thought it was legit. Took another like 300 years until people actually developed enough for you know, it to become more mainstream and trusted, right? And it took, you know, guys like Bernoulli and Gauss and Euler, Lagrange, Hamilton, all kinds of cool stuff going on. In fact, in the 1600s, it was introduced in the 1500s by Cardano. The 1600s, Descartes thought it was a joke. It's where the imaginary comes from. Cartesian coordinate system, Descartes. Anyway, he rejected it, but eventually, a couple hundred years later, you can take Math 360 and learn a whole lot about complex numbers. It's super cool, super useful. We're going to see one use of them in differential equations here. Now let's do a little bit more with some complex number ideas, right? So we already talked about, oftentimes we'll use z to represent a complex number. Then if I talk about the conjugate of z, then that would be a alpha minus I beta if z is alpha plus I beta. Right, this is the same as if I put the whole bar over that guy. Okay, that's the conjugate. What happens if we multiply z times its conjugate? Okay, so let's see, we would have alpha plus I beta, alpha minus I beta. Okay, well, let's just FOIL this on out. Okay, now we're going to talk just a little bit about more definitions of things, but if you just went on and FOILed, what would we get? Alpha times alpha is alpha squared, right? Then what? Plus I times alpha times beta, yeah? Minus I times alpha times beta. Then, whoops, minus, right? Minus I squared beta, yeah? Ooh, what cool thing happened here, right? Plus I alpha beta, minus I alpha beta, so what am I left with? Alpha squared minus I squared. What is I squared? Yeah, -1, right? Times beta, so what do I have? Alpha squared plus beta squared. That's a pretty cool thing. Yeah, all right, we'll look at more of that someday. What else do we know? This is a real number, right? It's a real number, yeah? And it's just the squares of these two guys that went in, yeah? And it doesn't matter whether we do it z bar or z bar z. Okay, what else? Suppose we have like 1 over a complex number, okay? Like 1 over alpha plus I beta, okay? What is that? Well, we often want to get rid of this complex number in the denominator, and so this is why we multiply by the conjugate, right? The complex conjugate. If we do that, multiply that. What did we just say? So you got to multiply by 1, right? Whatever you do the top, you got to do the bottom. So we pick the complex conjugate so that the bottom becomes what? What did we just say that is? Good, alpha squared plus beta squared, a nice real number, right? Now the top is still alpha minus I beta, and so you would divide and you get alpha over alpha squared plus beta squared. That's the real part of 1 over a complex number, minus beta over alpha squared plus beta squared I. This is the imaginary part of 1 over the complex number, alpha plus I beta, right? So fun with complex numbers, lots of fun, lots and lots and lots of fun. So let's talk a little bit more, diving into the world of complex number algebra, okay? Okay, so a little more complex number algebra ideas. Okay, two complex numbers. Make that like simpler. Two complex numbers. Let's say Z1. Let's just call it now A plus BI. A plus BI. And Z2, A minus BI. So we have two different complex numbers. Oh, sorry, no, I'm not doing complex conjugates now. Just two different complex numbers. C plus DI, okay? So what does that mean? A and B are real numbers. C and D are real numbers. I is our guide, right? Okay. Electrical engineers often use J for I, but what electrical engineers know? Anyway, here we go. The two complex numbers, Z1 and Z2, are equal. Are equal if and only if the real part of Z1 is equal to the real part of Z2, and the imaginary part of Z1 is equal to the imaginary part of Z2. Okay, so two complex numbers, Z1 equals Z2, right? If and only if this, right? So the only way those two guys are equal is if A is equal to C. For the above, A has to equal C, and B has to equal D. Okay. Now, your book also uses other notation for complex numbers, which is also common to be used as well. And so don't get too confused. We could also represent a complex, maybe I'll do it in blue. We could also represent a complex number Z1 as an ordered pair, A comma B, right? And what we mean is A plus BI. We're just giving the real part and the imaginary part. So the real part is here and the imaginary part is there, okay? This is not an ordered pair in the Cartesian plane, okay? But in complex variables, you'll learn how to exploit these ideas of thinking about an imaginary axis as well. So we could call Z1 A comma B, and then we could call Z2 C comma D, right? That's another way to write it, okay? So you just know that you're talking about complex numbers, then you know that this really means this. I'm not talking about an ordered pair in the real Cartesian plane. Okay, and so then you would say, right, A comma B equals C comma D, right? If and only if A is C and B is D. Yeah, does that make sense? Same deal, okay? Just a different way to write it, so don't be afraid of that. What else? Now, so we got equality, okay? So we talked about equality. We're going to look at just three things: equality, sums, and products. Okay. Now we just foiled right away here, so probably ought to just talk at least a little bit about what a product is. All right. So what if we're going to do a sum? Right? How do we add two complex numbers, Z1 plus Z2, right? Okay. Well, I add, if I go with those two guys, I add the real parts. So A plus C, and then my imaginary part is the sum of the imaginary parts, B plus D, right? Okay. So the sum of two complex numbers is the sum of their real parts plus I times the sum of their imaginary parts, right? Okay, that's what it means to add. And so in the book's notation, you would see Z1 written as AB, and Z2 written as CD. And how do I add these two things? I add them by saying I add the first guys, and then I add the second guys. Right? These two statements are the same with Z1 and Z2 given these guys. Right? Yeah? Okay. So when I add real parts, and then I add imaginary parts. When we multiply, it's a little bit different, okay? We don't just multiply real parts and multiply imaginary parts for the same reasons that we kind of saw over there. So what if we're going to multiply two complex numbers? So here's a product. The product of two complex numbers. So what do we have, right? We've got A plus BI times C plus DI. And it's the same idea of your FOIL, which is just a distributive law across each piece, right? Distribute A across each thing plus distribute BI across each thing, right? Okay? And so let's just go ahead and do that. We'll do it in a FOIL way, A times C, right? Plus B times C times I, yeah? Plus A times D times I, yeah? Plus B times D times I times I, so times I squared, right? Okay, well, what is that? AC, what is I squared? -1, right? I squared is -1. So if I'm going to gather these up and put the real parts of this product in the front, this is going to be AC, and then what? The real part? Good. Minus BD, right? AC minus BD, because I squared is -1. Now we have just these guys are just real numbers, right? That combination. And it's only these two guys then that have an imaginary piece associated with them, yes? So now let's do that part. So we get that plus, okay, I'm going to factor out the I, right? So what is I multiplying, right? BC plus AD, right? Or AD plus BC, and I'll just do it as AD plus BC to keep with. It doesn't matter, both are the same, right? Because they're real numbers, and you can multiply and add real numbers by switching the orders. And so we're here, and so this is what comes out of multiplying two complex numbers that have these real and imaginary parts, okay? And we saw that for a special case here when we multiply a complex number with its complex conjugate, what happens, the imaginary part cancels and we're only left with just the real part. That's super cool, okay? In the book notation, what does this look like, right? How do you say Z1 times Z2? So Z1 is A comma B times, using the big X for times, C comma D, that's what you'll see in the book, okay? And so then you see this definition here, that this is what you get, right? So you're gonna write this as an ordered pair, well, not an ordered pair, a complex conjugate pair, right? So what is the real part? The real part is AC minus BD, right? This guy times this guy minus this guy times this guy. It looked like it just came right out of thin air, right? In, you know, the definition of this is how to multiply AC minus BD. It looked like it came right out of thin air as a definition as to why would you do that, but hopefully this makes more sense. And then what is going to be the imaginary part of multiplying these two, using this representation for multiplying these two complex numbers? Well, I'm going to do this guy times this guy plus this guy times this guy, right? Okay, AD plus BC. So that's using the notation written this way, but hopefully you see it where it came from written this way. And maybe that will help it make a little more sense, okay? Let's explore this idea a little bit more with our guy I. So I think I'm definitely going to end this video after we finish this discussion to let a little of this sink in for you all. And so we'll be coming back to our other problem. We start going to have finished that guy. So we'll just have to, you know, wait on the conclusion of the cliffhanger as to how we solve an actual ODE, but getting a little more comfy with complex algebra is probably a good idea as well. Having a slightly better understanding of I, slightly, because this is all we're going to be able to do, is better than nothing, right? Okay, so let's talk about our guy I, right? Okay, so what is I? So back to I. Okay, so I is a complex number. It's a purely imaginary complex number, right? So if we write it in the a plus bi format, it's 0 plus 1 times I. Yes? Excellent, right? Okay. Has a real part that's 0, an imaginary part that's 1. Okay. Well, so then I is 0, comma 1 in this notation, right? A real part that's 0, an imaginary part that's 1. Yeah? Okay, we okay with that? All right. So now let's look at I squared, right? Well, I squared then is I times I, right? Well, that's a product of two complex numbers, right? And I is what? It's 0, comma 1, right? And now, right, since we're using this notation, we'll go with the times like that, right? 0, comma 1. It's just another way to say it, right? This is not the 0, comma 1 in real number ordered pairs, right? So we got this. So how do we multiply these two things? Well, we can use this format, right? Yeah, okay. So what does it say? This guy's going to this guy, a times c, which is 0, right? Minus the second guy times the last, you know, the product of the two second guys, b times z, so minus 1, right? 0 minus 1, that's coming from that, yeah? And then a times d, right? So this guy times this guy, so 0 times 1, right? Plus, what else? C, b times c. This guy times this guy, right? These middle guys, right? 1 times 0, yes? Okay, well what do we get? What is 0 minus 1? Negative 1. And then what's over here? 0 times 1, which is 0, plus 1 times 0 is 0 plus 0 is 0, right? We get negative 1, 0. What does negative 1, 0 mean in this notation? See it? Right? What does negative 1, 0 mean? Right? That's just the number, the real number, negative 1, right? Because the imaginary part is 0 of this number. Yeah? Okay? And so once again, we see I squared is negative 1. So under this definition of how to multiply an object that looks like this, we also come up with the idea of a quantity whose squared is, a quantity whose square is negative 1, which changed the world. Okay, let's just do a little bit more, and then we'll call this done. All right, so that's super cool, right? Super cool. Let's recall. So if, now we're kind of heading back toward our ideas of polynomials now for R. So we're gonna make our way back toward what we originally started thinking about, but this was good for you to get a little bit broader view of what of various ways to think about our guy I, right? So if R is a real number, right? And I have the polynomial r squared minus 1. I have this equation equal to 0, this quadratic equation, right? What would you do to solve that quadratic equation? Yeah, you wouldn't bring the one across and then root both sides, right? You would factor r minus 1, r plus 1 is equal to 0, and get that r is equal to 1 and negative 1. And so we get 2 real roots, right? 2 real roots. R equals plus and minus 1. Real numbers, right? Yeah, good. Awesome. Now, again, if r is a real number, and instead of r squared minus 1 equals 0, we have r squared plus 1 equals 0. If that minus is a plus, then what would you do to solve that equation? What would you do? If r has to be a real number, what would you say? You would say there's no solution, right? There's no real solution, right? So if r is a real number, the answer to this is no solution. Why? This side is positive, this is 0, right? Positive cannot equal 0. There is no solution, right? But if r is a complex number and r squared plus 1 is 0, well, now what? Well, this factors now. What does it factor to? What does it factor to? R and R. If we do it the same way, doesn't matter. Minus I and plus I, right? Look, this is a sum of squares, r squared plus 1 squared. What was here? What was there is alpha squared plus beta squared, right? If we do alpha plus I beta times alpha minus I beta, if we multiply complex conjugates, right? These two are complex conjugates of each other, yeah? The real part is r, and the imaginary part is 1, yeah? Okay, and if that's the case, what are our two r's? Well, this guy says r is I, and this guy says r is negative I, right? So what do we get? We get two complex valued solutions, imaginary in this case. So if we're in the complex numbers, this guy factors and we have two solutions. If we're in the real numbers, this guy has no solution. You guys probably would have done this, r squared equals negative 1. And then say r is the square root of negative 1, and then maybe say r is I, right? But r is plus or minus I. Yeah? Make sense? Okay? Right? Okay, so, this is pretty cool. Right, this is pretty cool. And I think we'll just call it here. There's so much more we could talk about. Of course, right, it is the square root of negative 1, but when you just constantly only refer to it that way and don't think about it in a bigger context, you just kind of lose track of what you're doing, really. So it's really a much bigger thing, and when we come back, we will then put these complex conjugate roots that come out of a characteristic polynomial to work for us to solve differential equations. Stay tuned.